All right. Hi, everybody. Thanks for coming. I'll tell you some news on the structure of the K-trivials. This is joint work with Greenberg, Miller, and Turetsky in 2 or 3 papers. Now I'm also contributed some source. Thanks for that. So before I start, I have to get this out of the way, the definition of Multilevel randomness. It's a central algorithmic randomness notion. Among the many ways to define it, here's one that's really short. The Solovay tests. So Z is multilevel random means there's a computable sequence of binary strings trying to approximate Z in a sense. The total measure cannot be too big, so the sum of 2 to the minus length of the strings has to be finite, and there are only finitely many i's, so that the I string is an initial segment of Z. You can think of this as an effective version of Vitali covering. The limit of the length goes to 0. If I view Z as a real number, which is just as fine, it means I cannot Vitali cover Z by those strings in the sense of infinitely often extending a string in the collection. All right, that's the main algorithmic notion, and we'll see that in some sense it's too weak. What does the Multilevel random compute? Well, if a set is given, call it A, then there's a Multilevel random Z above A. That's the Kuchera-Gach theorem. Draw a bit. If the set is delta 2, then I can just take Chaitin's omega, the halting probability of a universal prefix-free machine. That's equivalent to the halting problem and therefore above all the delta 2 sets. So that was easy. There's always a random above. Well, we'll ask how random is it really? For instance, if the given set is incomplete, can I make the random Turing incomplete? Answer no. Also, we can ask conversely, if I'm given a Multilevel random, which sets are below it? Kuchera proved any delta 2 random has incomputable CE sets below. In fact, he proved it for D and C, Z, which is more general, but the proof is especially nice for random Zs. So there's some non-trivial information below a delta 2 random. In fact, you can take several Zs and still get something below all of them. So that's sort of the initial result. And it says already that the C sets and the randoms interact nicely. The question is, how complicated can such an A be? All right, ML will always stand for Multilevel, and MLR is the class of Multilevel random sequences, frequent notation. Now, there's something I called a randomness enhancement principle way back in 2010, and it means among the Multilevel randoms, computationally weaker means more random. In particular, if Z computes less, then it gets more random. So that means if Z gets more random, then it should compute fewer CE sets in particular. And in fact, if Z is sort of very random, namely weakly 2 random, which by definition means it's a known null pi02 class. Or for the Multilevel test definition, the measure of the component goes to 0 as slowly as it wants. These sets are characterized as the Multilevel randoms that form a minimal pair with 0 prime. So nothing below them. In particular, they are not delta 2. Weakly 2 random could sit out here. All right, and that suggests the spectrum sort of between omega, or generally Martin-Löf randoms, which can be Turing complete, and the weakly 2 randoms, which compute nothing but the computable sets within the CE sets. Or even delta 2 sets. All right, so we have to somehow get into this spectrum of understanding the degree of randomness by how much our sets compute. So let's turn the thing around and start from the sets being computed. They're all k-trivial. I'll define this shortly. The k-trivials are the anti-randoms, which means, well, the k complexity is as low as it gets. K of a string is the prefix-free initial segment complexity. Schnorr-Levin says Z is Martin-Löf random if and only if K of the initial segments is almost maximal, so at least n minus constant. That's what this funny plus up here is trying to say. K-trivial is the dual opposite, so the initial segment complexity grows as slowly as it could possibly be, namely only the length matters. Clearly a computable set is k-trivial. Chaitin introduced this notion quite early on in 1975 and showed these sets are delta 2. Solovay, pretty much the same year, showed such a set can be non-computable. That was hidden in a manuscript that got almost forgotten and only resurfaced in the early 2000s. Yeah, so I'll tell you what results happened. A and B will always be k-trivials, and Y and Z will be Martin-Löf randoms. Those are my main players. I always want to look at sets lower down and how they compare to randoms, which are in some sense higher up. Any questions? Well, these results are pretty dated now, but still important for what I say. There were lots of characterizations of the k-trivials in terms of relativized k and in terms of relativized Martin-Löf randomness. So A is k-trivial just if k with oracle A isn't essentially less than k, A is helpless there, or A doesn't recognize more regularities in a set than the empty set. So it doesn't make MLR smaller. That's called low for Martin-Löf randomness. And in this advances paper 23, I proved a number of results relating k-trivial to Turing and other computability notions. The notion is Turing invariant. Every k-trivial is super low. They form an ideal. And also every k-trivial is below a CE k-trivial. So, yeah. So in this picture, A is not k-trivial. This is an ideal in the super low sets. And each such A, even if it's just delta 2, is below a CE set D that's also k-trivial. Essentially, it's a CE notion. Another notion that was already present in Kuchara's work from quite a bit earlier is basis for randomness. So now I want to know, is there a Martin-Löf random in A that also computes A? Such things are called bases for randomness. And this paper HNS 26 showed that that's again the same as k-trivial. One direction was known already because, well, if A is k-trivial, then it's low for randomness. And by Kuchara-Gach, it's below some Martin-Löf random Z, which is then also Martin-Löf random in A. but the other direction took a bit more work, the so-called hungry sets construction. Another result in that same paper that will be important for us says, well, under certain circumstances, I don't really need that Z is random in A. It happens automatically. Namely, if A is CE computed by Z, that's Multilevel random, but not Turing complete. Then already Z is Multilevel random in A. That happens by converting an MLA test into an ML test using those hypotheses. And this means A is K-trivial. So I don't really need MLRA in these circumstances, and sort of almost characterize K-trivial by just random and computability notions. To turn this around, if A is CE but not K-trivial, then there's no randoms above it that aren't anyway above 0 prime. So that means Kuchera-Gatch doesn't work in the incomplete randoms, also called difference randoms by work of Ling and Franklin. So if you want to see a picture of that here on my real whiteboard. I've made one. So if these are the K-trivials, and it's my old-fashioned pointing stick. Here are the K-trivials, A sits outside of the CE. Then this cone here does not contain any multilevel randoms. They all sit up here. Right. Well, now we actually can characterize the CE K-trivials in terms of just plain multilevel randomness by doing the converse direction. And that was supplied by 7 people in cohort, all these names in 2 different papers. In fact, for a C set A, it's equivalent to say it's computable from some incomplete multilevel random and saying it is K-trivial. And even more, there's a single delta 2 multilevel random above all of them and not complete. So they're all K-trivial because of that incomplete fixed multilevel random in subsets. All right, let me draw the set. There's some incomplete Z, also delta 2, sitting above all the K-trivials. That's the result from 2016. Well, what now? Reducibility I'm going to introduce now helps to understand the structure of the K-trivials from inside. The situation in 2016 was there's this class sort of crying out, hey, I'm here, I'm here, I'm here, in this way, in this way, in this way. But somehow nobody actually knew what the class looks like by itself. What's the internal structure? The only thing that was known is what I said already. Ideal, contained in superlow, generated by its CE members, and also there's no greatest degree in Turing. And I like to think this is because we had the wrong reducibility. In some sense, Turing is too fine to understand the structure. We're staying too close to it, too close to it. We don't see the forest for the trees. So we have to make a coarser reducibility. And what we take is already suggested by the results I've just given, ML reducibility. Here's my main definition. Given A and B, B is ML above A if any multilevel random that computes B also computes A. the cone above B in terms of multilevel random is contained in the cone above A. Okay, that's the main definition. I can phrase this in the sense of two aloneness paradigms. The common one is computational aloneness means not being very useful as an oracle. That gives just the usual aloneness, super aloneness, and other notion I've mentioned. If you turn this relatives into reducibilities, then you get weak reducibilities such as LR, and we'll later introduce SJT reducibility, also following this paradigm. But that's not the one ML is based on. ML thinks of a set as low if it's easy to compute. There's many, many oracles computing it. And in this case, B is above A because fewer sets compute B than compute A, all randoms. It's a different paradigm. And some facts on these degrees right away. First of all, the whole thing collapses within the C sets to the K-trivials and omega, which I haven't even drawn here. So omega sits up here, everything non-K-trivial collapses to omega. And so this naturally tells us just look inside the K-trivials. Second. Yeah, so, and another result that's actually useful and important for this work, any K-trivial A is ML equivalent to a CE K-trivial. Call it D, and D is also above A, improving the result that some K-trivial above A is CE. It's actually in the same ML degree. That simplifies a lot of results earlier on where we had to make special distinctions for CE and then generalize to the case of the other two. Let's understand the structure using ML equivalence. The least degree is merely the computable sets. Simply by low basis and upper cone avoiding. Any non-computable set has a random not above. So that was easy. However, there's also the largest ML with respect to ML K-trivial, which we found in that 2016 paper and called smart K-trivial. K-trivials aren't overly smart, but among those not so smart, it is as high as it gets. Smart sits up here. So there's an ML complete K-trivial. Now about the structure inside. In the later paper with Joe and Noam, we found a dense hierarchy of principal ideals, parameterized by rationals between 0 and 1, excluding. What are these? Well, say Q is 1/2, take all the sets that are computed by both halves of a random. The halves meaning, well, the bits in even positions and the odds bits in odd positions. Kuchero already knew that, well, there's something below both halves of omega. So make this your class. It doesn't really matter which random you take. That's another result along those lines. So this makes a principal ideal sitting further down, as I will show you. These are what we call the 1/2 bases, meaning below both halves of omega, say. And so on. For any Q other than 1/2, there's yet another ideal, and they all have a largest element. So there's quite a number of natural, if you want, at least special ML degrees. Many other interesting subclasses are at least downward closed. For instance, SJT, strongly untraceable, conjectured not to have the largest element. I'll define that shortly. It means the set can approximate the jump. You can approximate the jump of the set with very few errors. Well, this property was shown to be equivalent to be below all omega CA multilevel randoms, and that shows it's an ideal in my ML degrees here. All right, so that's the structure, and now also we can do a bit of degree theory inside the K-trivials. Here's the definition again. Using methods of Kuchera combined with permitting any non-computable CEK trivial has a pair of ML incomparable CE sets below. And in fact, the witnesses for incomparability are delta 2. There are no minimal pairs. And well, ML degrees are pretty big. If I give you a CEK trivial, say there's another K-trivial in the same ML degree, but strictly above in the Turing sense. Stop for a moment. Any chats, any questions? Oh, share the whiteboard for the latecomers. Here it is. So you can scroll up and down. You can even write into it. All right, so we're doing the degree theory. 2 and 3 are based on cost functions. We don't know density. And well, we don't know a lot about ML at all because it's not clear whether it's arithmetical. The definition makes it pi11. So any construction with requirements would need some kind of reductions. And so it's hard to see what a construction showing they are dense looks like. The arguments up here are sort of ad hoc, working just for the particular problem. I can restrict my randoms to delta 2, and most of the results are saved because that's of course arithmetical, but it's not quite clear whether density works here. All right, so that's ML. And now I want to tell you about the main tool used for all these results, cost functions. I introduced those early on as a way to generalize a lot of constructions of sets with lowness properties. And here's the definition. The cost function is simply a computable function from numbers, pairs of numbers to the non-negative reals. Usually we want requirements saying it's nice, so it goes down in X, goes up in S. X is sort of a number you want to assign a value to, and S is the stage in a construction. The eventual cost will be finite, and the limit of costs over larger numbers should be 0. Now, if I have a computable approximation of a delta 2 set and a cost function, I can define the total cost C of that approximation, which is the sum over all costs of changes, or not quite, actually least changes only. So look at all stages S and see what's the least number that changes in value, truth value, and count that. To obey a cost function means there's some computable approximation making the total cost finite. And briefly, I write A model C or obey C. The basic existence theorem says for a cost function with these properties, a CE and in fact promptly simple set obeys it. So a non-computable or in fact promptly simple set obeys it. A cost function is a bit like a speed limit. It tells you, well, you can approximate your set, but don't change too much or too fast. Drive slowly. A cost function that actually came up quite late is COmega. Simply take Chaitin's omega and left C real, and C omega of xs is what omega is at stage s minus omega x. That clearly has all these nice conditions. And reviewing constructions from earlier on in a paper that only came out in 2017 in the incomputable, I showed a delta 2 set is k-trivial if and only if it obeys C omega. Of course, this was known long ago, long earlier for a variant CK, which is not quite as neat, but directly shows why a set obeying it is k-trivial. That's in my and Dennis and Rod's book already. For another example, how ideals can be characterized using cost functions, like let's take the half-bases again. Remember, we want to look at sets that are computed by the even and the odd bits of omega, say. In this paper that came out in 2019 in JML, Joe, Norm, and I proved that the right cost function for that is the square root of C omega. Okay, that means bigger, meaning more expensive. So it's harder to construct these sets. They're lower down, as you see in my diagram. This is exactly the sets obeying C omega 1/2. And you might guess there's a general theorem saying there's the biggest set with respect to ML for each cost function. And yes, there is. I'll tell you shortly after a few definitions. The nice thing is we can not only just say delta 2 set obeys C, we can also think of random sets obeying a cost function with a different definition, but related. So if you think of Multilevel randomness, you have these tests, the uniform collections of sigma n sets, sigma 1 sets, so that the n set has measure at most 2 to the minus n. And now we look at a more general test, call it UN, and the convergence of the measure to 0 is bounded by C bar, where C is a cost function. C bar, remember, is the limit. Let me write it again. If C is a cost function, C bar of n is, which is finite. And that goes to 0, which means that if I have a C test in this sense, then the measure will go to 0, just more slowly. The main fact, really the fundamental fact, which was already present in Kuchera's construction, that a delta 2 random computes an incomputable CE set. The basic fact is this: if C is captured by a C test, C is Multilevel random. That's what it means to obey C. It's captured by a C test. It's not too random. If Z is of that kind and A obeys C, then A is going below C. A is going below Z. Nothing could be easier. So Z up here obeying C, A obeying C in its way, A has to be below Z. Why is that? Well, we make a Soloway test of wrong oracles. If A changes, then some oracles become invalid in a reduction I'm building, which has identity or +1 use actually. So if that happens, then I list UNS as a component of a Soloway test. Z is random, so it has to be outside almost all of the components, which means it will correct almost all values of A, compute correctly. The full proof is probably a third of a page printed. Okay, so that's the basic fact. And let's now define Multilevel completeness for a cost function in general. C is a cost function, always at least COmega, meaning what obeys it will always be k-trivial. A is smart for C if it's ML complete among the sets obeying C. In my picture, the various things at the top here will be simply the smart ones for the cost function characterizing this class. For instance, for the 1/2 basis, I have C omega 1/2 for all k-trivials. I have C omega. Like this, okay? All right, so smart for C means ML complete among the sets obeying C. In other words, any B obeying C is ML below A, and A obeys C itself. Our result here in the GMNT paper, Greenberg, Miller, myself, and Turetsky on archive extends the result in the 2016 paper only for the k-trivials. It says every cost function has a C set that's smart for it. And that extends the basic construction that some set obeys the cost function and is not computable. There's actually some set that obeys it and is as big as it can be among those sets. Just the main elements of the proof, which isn't very long. We can assume C of k is at least 2 to the minus k. We build A. It's enough to look at one Turing functional, appropriate one. And what you have to do is if A is below y via this functional, then y fails some C test. Why is that enough? Well, why is it enough? Well, by what I've told you. If B obeys C, then, well, B is Turing below this y, because y obeys it and B obeys it. So the basic fact says B is below y. That's all I wanted. If y is above A, it's above B. So B is ML below A. Because I really catch all y's up to finite differences. It's enough to look at gamma. Oh, sorry. All right, so what do? We build a C test as required. The test is more or less written here. For each k, g, k, s is all the y's, so that gamma y t up to 2 to the k plus 1 is defined in an initial segment of at for some t between k and s. I update this during the construction. I have an error set, namely the y, so that AS has already moved beyond what y computes. A is CE, so once it's to the right, this is gone. So that's the error set. And we ensure that the measure of GKS is never bigger than C of KS plus the error that entered from K on in measure. If that seems to go wrong, we put the next number into A from the interval assigned to GK. And that does it. There are enough x's because of this condition. And By that definition, GK is a C-test which captures Y, and AO based it by some calculation because of this error set, and things that go in are disjoint from what was there before. It's a pretty nice and short construction, and shorter than the original one. All right, so that's the smart for C set. There's a corresponding result. When I've given a set A, I can make a cost function that is smart, so that A is smart for that cost function. Now I'm given a set A, all I want is k-trivial, and I can build a cost function. And that's used to show some of the results I had mentioned on the degree theory. For instance, to show there are no minimal pairs, take non-computable k-trivials A, B, look at their cost functions, add them up, which makes it harder, but there's still something obeying their sum. And then, by a simple argument, that set, which is incomputable, is ML below both A and B. Okay, let's look through results related to that on half-bases. So my diagram already suggested that half-bases are strictly stronger than just k-trivials, and that's below because even and odd bits of omega each form a low set, but also something captured by a COmega test, not over referendum, must be super high. So the smart thing for k-trivials up here cannot be a half-base. But we don't know much else about it currently, such as which other cost functions can it obey, how much more expensive can your cost function become till it's impossible. It's not quite known. Also, there's a way to understand the complexity of randoms now through the k-trivials they compute. Just the dual reducibility. Z is ML star below Y if each k-trivial A below Z is also below Y. And the notion dual to smart, well, some people suggested dumb or even retarded, but let's call it feeble. Z is feeble for C if it's captured by a C test, and among those sets has at least ML star degree. So that means anything below it is only there because it obeys the cost function. It only computes the things that have to be there by cost function reasons. So the P part of omega is feeble for a cost function C omega P, which is the P's root of omega. It's pretty clear what the P part should be for a rational, but I won't define it. The top degree is all the randoms that aren't very random, namely that are captured by a COmega test. Remember, higher up means less random, so the top degree is reasonably the things that aren't too random, and the bottom degree is the very random things, namely the weakly two randoms, which don't compute anything in the data two sets, except the computable ones. Given this notion, we have given quite a detailed analysis of the pieces of omega under ML star, which gives the dense hierarchy here and sort of a dual dense hierarchy of random sets sitting somewhere up here. So if R is an infinite computable set, omega R is the bits with position in R. C omega P has a generalization, C omega R, and A obeys that cost function just if A is below omega R. And that means omega R is feeble for its cost function. The general theorem gives equivalences of when one piece of omega is ML star below another piece of omega. Let's take a smart K-trivial for COmega_R, where R is an infinite computable set. And now we have three equivalences for infinite computable sets R and S. Omega S star below omega R, BS ML above BR. So those are like, well, not quite brothers, but this is the low guy and this is the high. But they are closely related. And also just the combinatorial property, S up to n has at most as many elements as R up to n, for any n up to a constant. For instance, if S is a subset of R, then this is trivial, and here we get Turing. So that makes sense. But in fact, I could just take the evens and the odds. 3 is certainly satisfied. So that implies, surprisingly, that the omega even and omega odd actually computes the same K-trivials. Before I'd always said below both halves of the random, but in fact, for omega, I only need one half to also get the other half. All right, so that's that. And in closing, I want to look at some variants of ML, other weak reducibilities. Weak means something like at least weaker than Turing and possibly more things. So the SJT reducibility I had already mentioned. Let's define that using functionals. It's an easy exercise that A is Turing below B, just if the jump of A as a partial functional can be simulated by B using a partial functional in B psi. But what if I just say, okay, B, you can have a few guesses, very few guesses for JAX. One way to make this formal leads to SJT reducibility. An order function is a computable function that monotonically goes to infinity. And A SJT below B means for any such function, there's a uniform list of functionals so that JAX is one of those. Namely, it's psi B R of X, where R is at most H of X. Plain SJT, introduced with Figuera and Stefan in 2005, is the notion A is SJT below 0. And people like Cholak and Greenberg and someone else, I can't remember. Oh, sorry, Downey, I think. Yeah, they showed that this is a proper subclass of the K-trivials. It's not that hard to see. It's actually transitive. You need to work a bit, but it's important that I don't just relativize SJT to B. I relativize only a part of it. For instance, I don't have JA plus B here, but only JA. That's a partial relativization, which makes it transitive. Relativizing that result, that the SJTs from a proper subclass yields that there's no SJT largest K-trivial. Different from the ML case. Let's talk about omega CA sets. Omega CA means, or is equivalent to being weak truth table below 0 prime, also known as omega CE, by the computable approximation that doesn't change too much. Here's the theorem characterizing SJT reducibility in terms of randoms. It's an almost theorem, not quite done in all detail. For any of the classes of omega CA or super low or super high sets, for any two K-trivials, CE say, for any two CE K-trivials, A is SJT below B, just if any Y in that class, that's Multilevel random, lifts B above A. Well, those are quite far because this has nothing to do with approximating the jump of A. It just says so A is computed by B and any omega CA random, say. In a paper with Dennis and Norm, we had done the case B equals the empty set. saying, for instance, SJT is the same as below all omega CA randoms, in the CE case at least. All right, so that's a result pointing to SJT, which is defined using the main lowness paradigm. We have now two weak reducibilities between Turing and this one, which says, well, any omega CA random computing B also computes A. Of course, that coarses ML, but also by this result, SJT reducibility implies that weakest version. On the other hand, ML and SJT are incomparable. So you could look at the structure inside the K-trivials with different eyeglasses and, or rather, from different angles. One would be ML, which is, I think, the most successful. But you can also look at SJT reducibility, in which case you get K-trivials here. And the lowest degree is just SJT. That's all collapsed, and you look at the relative complexity under that reducibility, but there's no largest element now. But there's still a lot of structures, a lot of structure there. All right, so that's a new paper with Greenberg and Storetsky. Here's a few questions. Well, is being smart among the K-trivials actually arithmetical? We have one way to make it, but there could be many others. And in fact, that's the weaker form of the question, whether ML is arithmetical as a relation. By definition, it's not, and it would give a significant different view of ML reducibility. For instance, in terms of cost functions. Again, are the ML degrees dense on the K-trivials? Say more things on the capable, on the smart K-trivials. And in terms of Turing reducibility, so can they be capable, for instance? The usual constructions will make them promptly simple. You have to put the element in right away to make it work. So we don't know this. And again, can it obey stronger cost functions? So study more of the smart K-trivials up here. And finally, can I make this Z here omega CA? The construction by Day and Miller, which was needed there, it builds by forcing a incomplete Martin referendum that's not a density 1 point, which implies not obeying, implies that it obeys the omega and therefore is above all the K-trivials. But the best they can do is make it delta 2. So it's the same question I asked at the AIM workshop, and it's still open 2 weeks later. Right, here's a few references, and that's it for now. And I'm open for discussion.
Thanks, Andre. I think if anybody's got a question, just please unmute yourselves and ask the question.
You have looked at the construction in the paper with Adam Day, and just to see, like, does it, like, how complicated does it look? I assume.
Yeah, it doesn't do it as it is, but you should be able to know, to tell me.
Well, I mean, I have to read the paper too. I don't remember everything.
Right, it's a while ago.
I mean, it's not even that long ago, but I have a very short memory. I'm a goldfish. But okay.
I don't believe that, but I think it's you need something else. You even have to work quite harder to make it delta 2, and omega CA is not there.
Okay.
But yeah, it would be an obvious approach to look at this closely and see how you can modify it. It's quite possibly not true that it's just there's no omega CA at all.